Let's do the easy one. The one on the left is easy. They're both easy. Let's do the one on the left because it's the one that you probably have the most chance of success. Net force equals change in momentum. I know the change in momentum of the ball. The ball has a velocity of 3 meters per second, then contacts the wall, bouncing off of it at 2 meters per second. I'm going to choose to the right to be positive. Change in momentum is mv final minus mv initial. You had to bring mv to the table here. I'm not asking very much, though. So that's going to be 0.5 times, well, the final momentum is 2, but it's in a negative direction, minus 0.5 times 3. That's it. It's going to be negative 2.5 kilograms meters per second. But that's not what I asked you. This is the impulse. I asked you for the force on the ball from the wall. Well, that's going to be net force times time, which in the problem you're told is 0.04. So 0.04 seconds. That's it. So you just solve this for net force. And net force equals negative 62.5 newtons, meaning to the left. The ball experiences a force to the left. Now, if your notes didn't help you there, why? Write it in now. If you want your notes to be helpful, which you had access to for this practice, what didn't you know that you need to know now? Put it in your notes. Make them useful. I'll wait 30 seconds. Some more things you should probably add to your notes. Things of value to me, but I'm not sure how you're going to put them in there. The ball was in contact with the wall for 0.4 seconds. It's important for you to note that during that time, so there's the ball in contact with the wall. During that time, the ball applies a force on the wall, and the wall applies a force on the ball. Those forces are equal and opposite. So the Newton's third law is as much about impulse as it is about force. So you should reinterpret Newton's third law to state that for every impulse, there's an equal and opposite impulse. And it's not a huge stretch, but it's important. The wall experiences the same impulse as the ball does, because they have to experience the same force. That's Newton's third law. And there's no way the ball can stop touching the wall without the wall also not touching the ball. So the time period always has to be the same too. Can you do this one? I'm going to give you a hint. It's a small hint, but you're supposed to know how to do things now. Right? This is no longer the beginning of the year. This is the middle of the year. I'm going to remind you that it's a vector problem, but as in any vector problem, you should choose directions that you call positive. I would probably call these two directions positive. It makes reasonable sense to do so. Now, from there, this problem is done exactly the same way as the other problem. This is still a net force times time. Impulse equals change in momentum. It's just a two-dimensional problem. Go on, give it a shot. You guys, let's pay a little bit of attention here. How about this? The initial velocity of the ball. When I look at it, I'm thinking it's totally in the y direction and in a positive y direction. So I'd probably write this as 0x hat plus 3 y hat. Right? Does that give you enough of a clue as to maybe how to write the final velocity of the ball? Try. All right, too much time. Did you get your 45 newtons yet? If you didn't, you're not really paying attention the way I'd like you to. I'm going to start with the same exact thing as I did before, net force times time equals change in momentum, which is going to be mv final minus mv initial. Let's see, m is 0.5, v final is going to be 2x hat plus 0 y hat minus v initial, which is 0.5 times 0x hat plus 3 y hat. I know you guys just love to throw away all the stuff we've supposedly learned earlier, but you do it so disposable, it just hurts my feelings. We're just going to subtract these two, and I believe we'll get 1x hat minus 1.5 y hat. This is the net force times t. This is the change in momentum of the disk. It's not hard. You guys don't remember anything from first quarter. Moreover, this says that the change in momentum has a component in the x direction and a component in the negative y direction. This is 1.5 kilograms meters per second, and this is 1 kilograms meters per second. They're just vectors. We just add them in 2 dimensions, suggesting that my net impulse is that way. Oh, it dawns on people. It's just a triangle. So yeah, Pythagorean theorem, inverse tangent, you can get the angle of this force, impulse, and you can get the size of this impulse. That's it. We don't throw away the stuff we've already learned. But I'm afraid you did not really internalize that stuff. We good? This is going to get you your 45 newtons. And yes, I expect you can do this kind of stuff. Right, this is why we learned how to deal with these vectors. So adding, subtracting vectors in your wheelhouse, correct? Let's put it back up there. New material today. Do you remember a while ago we talked about center of mass? Good, good. Again, I don't want to be throwing away stuff, but there's some stuff that we have to be reminded of. I want to talk about the motion of the center of mass. You see, one of the things that we are dealing with when it comes to impulse is that impulse can be talked about on an individual object basis, but can also be talked about as it applies to a system. So you can apply an impulse to a system, a collection of objects. But, and this part I think is critically important, if the net force on a system is 0, if the net force on a system is 0, then the change in momentum of that system must also be 0. So the momentum of the system does not change. Now, how that plays out is critically important, and I want you to consider this reminder of center of mass. So imagine that we have 2 cars. So taking too much time to draw stupid cars, but I want to draw cars. There we go. 2 carts. If I asked you to calculate the center of mass of the system, what information about the carts would you need? Go ahead. I would need the location of the cars, or the separation distance of the cars, and what else? Go ahead. The mass of both cars. Let's say the cars are 0.5 kilograms and 0.75 kilograms. But unfortunately, let's say that one of the carts isn't staying still, but is moving at 2 meters per second. Is the center of mass of this system staying still? No, the center of mass of this system is changing. So one of the things we could talk about is deal with not the center of mass of the system, but the velocity of the center of mass of the system. I want you to consider that this would just be the center of mass of the system divided by t, right? The rate of change of the position of the system. And if you don't like that, a better way of saying it is that it would be d dt of x center of mass, but I don't think you guys like that at all. But this would be the derivative of the position of the car with respect to time. But it's just also dividing by a time interval. How does that position change? So delta x over delta t. Does that make sense so far? Want to find the velocity of center of mass? Well, I remember the center of mass formula. Do you? Good. Tell me.
It's the sum of all the it's the sum of the masses and the position of the masses, like maybe your reference point,
Mm-hmm.
and then under the sum.
Just throw it anywhere.
Under the sum of all the masses.
Okay. Something like that? All right. Well, if that's center of mass, if I divide this by t, I wouldn't be dividing top and bottom. I'm dividing the entire thing by t because I want this to be the velocity of the center of mass. Then this would just change and be the sum of mi vi from first object to last object divided by the total mass from the first object to the last object. This would be how you would calculate the velocity of the center of mass of the system. The position's always changing, but if you know the speeds, you can figure it out. This does make a huge assumption. It makes the assumption that the velocity of the system is constant. And that's the level that I want you to be able to work at. I want you to be able to find the velocity of the center of mass if all their velocities are the same and not changing. Does that make sense? Okay, what's the velocity of center of mass of the system? I don't believe so. Not based on what's here, because one of the objects isn't moving. So if I was to calculate the velocity of the center of mass of the system, I have to add up mv for each of the objects. This is actually adding, if you look closely, this is adding the momentum of all the objects together, right? So the first object would be 0.5 times 2 plus the second object, which is 0.75 times 0. Sum of mv for each object in the system. And then I would divide by the total mass of the system. This is the velocity of the center of mass, which 0.8 meters per second. Got it? Not particularly hard to do? I need you to tuck that away for just a minute. This whole idea of the velocity of the center of mass. And take a second, clean up your notes, make sure they tell you how to calculate the velocity of the center of mass and how it's different from the center of mass location. Make sure you have that in your notes, because right now you probably just have all this gobbledygook. Write some words down to help you. I can wait 30 seconds. What we really need to talk about are collisions. I mean, clearly we've set up a collision here. In a collision, one object interacts with the other. There's going to be forces applied. In fact, in this particular instance, I think it's pretty clear what's about to happen. After a few moments, this car is going to come in contact with that car. Correct? There's going to be an interaction, an exchange of momentum. The 0.5 kilogram car is going to apply a force to the 0.75 kilogram car. And at the same time, the 0.75 kilogram car is going to apply a force to the 0.5 kilogram car, right? Those two forces are going to be equal and opposite, which means it's going to spawn two equal and opposite impulses, which means the 0.75 kilogram car is very likely to gain momentum at the expense of the 0.5 kilogram car losing momentum. If this condition holds, that there's no external force on the system, then the change in momentum for this car has to be equal and opposite to the change in momentum for that car because of Newton's third law. Right? Newton's third law states clearly that there will be an equal and opposite force, and therefore an equal and opposite momentum. I'm sorry, equal and opposite impulse. That means an equal and opposite change in momentum. Now, I don't want to make this super hard because it's not particularly tough. But if we look at this, if this is car 1 and this is car 2, then I have P final for car 1 minus P final for car, P initial for car 2. Initial for car 1. All the P1s on one side equals minus P final for car 2 minus P initial for car 2. Now, if I distribute that negative sign, right, distribute the negative sign, collect terms, I'll get P final for car 1 plus P final for car 2 equals P initial for car 1 plus P initial for car 2. So what this says, if you're paying attention, is that if there's no external force on the system, there can be no change in momentum to the system. The momentum of all the objects before the collision have to be equal to the momentum of all the objects after the collision. Momentum is a conserved quantity if there's no external force acting on the system. So those external forces, things like friction, things like gravity, these are all external forces. They would change this. But if there's no external forces on the system, momentum is a conserved quantity. So now that we have all three kinds of collisions, let's practice with a couple of different scenarios. So let's set up a scenario using what we have here. Here's our first scenario. And I want to take this this velocity of center of mass and just kind of tuck it away for a minute. And this stuff you should probably just have down here to be thinking about. But this is our initial state and our final state. Let's start with a perfectly inelastic collision, shall we? Pretty straightforward. They're going to stick together. In a perfectly inelastic collision, the momentum before the collision has to be equal to the momentum after the collision. You're just going to add up the momentum of all the objects in your problem. Momentum 1, momentum 2, and set them equal to the momentum of all the objects after the collision. Right? That's what this says to do down here. So momentum is just mv. So 0.5 times 2 plus 0.75 times 0. That has to equal, well, in this particular case, the two objects stick together. So they're going to have the same final velocity. In fact, I would just put that in parentheses, 0.5 plus 0.75 times v. Now, this answer shouldn't surprise you. Buzz through it real quick. You've already done this, but buzz through it real quick. Did you get your 0.8 meters per second? You should, because that's the velocity of the center of mass, right? If these two things stick together, they're one object. They have to be traveling at the velocity of the center of mass. It makes reasonable sense. Let's try a different one, though. We all good here? That was a perfectly inelastic collision. All right, we set the momentum before equal to the momentum after. So let's try a different scenario. What if instead the cars don't stick together and this car moves off at 1.2 meters per second? But we don't know how fast or in what direction this car goes. Now, one thing I want you to be careful about, because I've been kind of playing a little fast with these rules, I established without saying that this direction is positive. when we're working these problems out, if you work out a velocity and it works out to be negative, it just means the object's going in the opposite direction. So make sure you are cognizant that these are vectors. Now, doing this problem does not change the initial information, right? We're starting with the same amount of momentum. Just in this collision, I switched the cars so it doesn't have Velcro to stick together, and now the cars separate. You're still being asked to figure out how fast one of the cars is going after the collision. This is probably an inelastic collision. I say probably because I don't know for sure. So we'll try it out. We'll have 0.5. 0.5 times my unknown final velocity plus 0.75 times 1.2. Do your arithmetic real quick. It's not hard. But you're going to find that the final velocity here, I believe, is 0.2 meters per second. I believe it works out to be positive. Now, you should take a quick minute and show that the velocity of the center of mass is still 0.8 meters per second. You should try it, just to make sure. And if you don't know what I'm asking, I'm saying take that equation for the velocity of center of mass, 0.5 times 0.2 plus 0.75 times 1.2, and divide by the total mass, 0.5 plus 0.75. I assume you get 0.8. You better. If momentum is conserved, the velocity of the center of mass shouldn't change. And you do. 0.5 times 0.2 is 0.1. 0.75 times 1.2 is 0.9. You get 1 divided by 1.25 again. It has to work out this way, guys. The top is the sum of the momentums. That's still equaling the same thing. Now, I'm not going to set up a elastic collision for you because the math isn't hard, but it generates two relationships and two unknowns. And one of them is a set of squares. It's a lot of math. You should look at one. But I will say you could be asked to verify whether a collision is elastic or not. It's right here. Right? All you would ask yourself is, how much kinetic energy did I have before? Right? That's the kinetic energy before. And compare it to the amount of kinetic energy you have after. Right? If they're equal, then you have an elastic collision. If the left side is greater than the right side, you have an inelastic collision. If the right side is greater than the left side, something added energy to the system. It must have been something that had energy in there.